Assalamualaikum and hello everyone. So today we continue with chapter 5, which is on finite length discrete sequence. Okay, what is the difference between chapter 2 and chapter 5? In chapter 2 you learn on time domain, which is in infinite length sequence and finite length sequence. Okay, so in chapter 3 you learn on the DTFT of infinite and finite sequence. Okay, in chapter 5 we just concentrate on finite length discrete sequence. When I say finite is all about the limited range, okay, of the sequence, for example from -3 to 3. Okay, while infinite length means we have the infinite range, for example like from infinity to infinity. So that is the difference between finite and infinite length. So in chapter 5 you will learn on finite length discrete sequence. Okay, so as introduction, okay, this one you can refer to slide number 2. Okay, mapping finite length in time domain to finite length frequency domain. So basically in chapter 5 you are going to learn on mapping the finite length in time domain. For example, we have xn equal to 1 to 3. The range is from 0 to 2. So this is considered as finite length sequence. Okay, so in chapter 5 we are going to determine the x exponent j omega of this sequence. Alright. Such collective known as finite length transform. Okay, since this Sn is finite length sequence, then this transformation is also known as finite length transform. Alright, so let's say we have a long sequences. So in this case, since we have long sequences, for example from -8 to 8, so it is a very long sequence. So to apply finite length sequence, what you have to do is, first we are going to cut sequences into short sequences. For example, instead of from -8 to 8, now we're going to have from 0 to for example 4 to -8, and -4 to -8, and then from -3 to 0, and then 0 to 3, 4 to 8. So we cut the long sequences become short sequences, and then we use finite length transformation process in transform domain. Okay, so after that, after we broke into short sequences, which is actually in time domain also, okay, and then we process in transform domain. Okay, all the processing must be done in frequency domain. Okay, don't forget about that. Okay, and then taking the inverse transform into time domain. So next what you have to do is we need to do inverse transform from frequency domain become time domain, and then the short sequences results are concatenated finally to get at the overall output. So basically for you to get the overall output, you have to combine all the short sequences. Okay, means all the process is done in parallel. One part, second part, third part, fourth part, and then combine all the from the first part until the fourth part become one. Okay, become a long sequences again. Okay, so next we refer to slide number 3. There are variety of finite dimensional transform, but in this chapter we concentrate on orthogonal transform. Example of orthogonal transform is discrete Fourier transform, DFT, which is usually used for digital signal processing application. And discrete cosine transform and Haar transform, which usually used for signal compression. So for DSP, we concentrate on DFT, used for digital signal processing application. Later on, if you're thinking to take image processing subject, okay, so you will learn on the Haar transform for signal compression and so on. Okay, but for DSP, you just learn on discrete Fourier transform. Okay, so what is orthogonal transform? Okay, let's say we have Xn denote a length n time domain sequence with Xk denoting the coefficient of its n point orthogonal transform. So in orthogonal transform, this is called frequency domain. This is called time domain. Okay, so in chapter 3, you learn on for you to find what is your frequency domain from time domain, you need to use DTFT. Means you have to use discrete time Fourier transform. So the keywords is Fourier transform. This is from chapter 3. Okay, in chapter 5, you will do orthogonal transform. Orthogonal transform. Okay, so instead of we use x exponent j omega, now your notation is x k. Okay, so similar to chapter 3, we have analysis equation for orthogonal transform. We also have synthesis equation for orthogonal transform. Okay, so analysis equation is meant for if you want to convert from time domain to frequency domain, the orthogonal transform. But for synthesis equation, you have the frequency domain of the signal, and then what you have to do is you need to convert to time domain. Okay, where if you look at this equation, we have the sigma kn. So sigma kn is called as the basis sequence with length n sequences in time and frequency domain. Alright, so if you look at this equation, these two equation is actually similar to our previous Fourier transform equation. Okay, so condition for orthogonality defined as, okay, 1n equal to this equation equal to when L is equal to K, the orthogonality is equal to 1, but it is equal to 0 if your L is not equal to K. So, alright, so in this chapter, in chapter 5, instead of we use orthogonal transform, okay, in chapter 5, we have DFT. So DFT is actually similar to DTFT, just that for DTFT, it covers finite sequence and infinite sequence. But in DFT, this part is just cover the finite length sequence. Alright. Okay, so we have the DFT of length n time domain sequence Sn is defined by xk equal to summation Sn exponent minus j to pi kn over capital N. So we have this equation. k equal to alright. So if you look at this equation, this is the DFT equation, means you want to convert from time domain to frequency domain. So in this part, you have seen exponent j2 pi k n over capital N. This capital N is number of sequence or length of sequence. Okay, let's see, we have xn equal to 1, 2, 3. So the range is from 0 to 2. So based on this sequence, you know that your capital N value is equal to 3. How to know that your sequence is 3? 0, 1, 2. So basically, your capital N is equal to 3. Okay, another way around, you can see the number of okay, you can see how many numbers inside the curly braces. Okay, for example, we have 1, 2, 3. So you have 3 numbers. So basically, your capital N is equal to 3. Alright? Okay, so basically, obtained by setting, okay, we know that, okay, we have something like sigma. I don't know what is the real symbol. Okay, please check again. So we know that sigma, this one, I call this one as sigma. Okay, please check. Equal to exponent j2 pi k n over n. Okay, so instead of we use this one, we use the common notation. Okay, so what we have to do is we use the common notation. We replace with Wn equal to exponent minus j2 pi over n. Okay, so what happened to this equation? Okay, this equation will become summation n from 0 to n minus 1. We have xn Wn. Okay, so we replace exponent minus j2 pi over n with Wn. So what's left is actually Kn. So we have this one. Alright, so this is DFT. Okay, so next we move to inverse DFT. Okay, in inverse DFT, we have to taking the basic sequence as, okay, we have this one. Okay, refer to slide number 7. Okay, you will see this one again. Okay, this time around, we want to find what is the inverse DFT. Okay, so if we want to find the inverse of DFT, you can see you will have the equation of 1 over n times summation from k from 0 to n minus 1 at k Wn minus Kn. Okay, why we have minus Kn for inverse DFT? Alright, because of we want to find the inverse. We want to find the opposite transform of the xk. So opposite transform of xk is xn. Since we want to find the inverse, the opposite transform of Sn, definitely instead of we use Wn Kn, now we use minus. Okay, another one is we have 1 over n. Okay, this one k from 0 to n minus 1 xk Wn minus Kn. So basically, since we are going to find the opposite of xk, that's why we have minus. Okay, and then here we don't have 1 over n for xk, but if you want to find for Sn, we need to multiply it with 1 over n. Why again? Because we need to find the inverse. Okay. Alright. Okay, we go next is discrete Fourier transform per equation. Okay, same thing. Okay, this is slide number 8 is actually the equation for DFT and the equation for inverse DFT. Okay, this one you can refer to your slide. Okay, so basically from the slide we know that, okay, by using common notation we have Wn equal to exponent minus j 2 pi over n. So class, make sure later on for chapter 5, this is the important equation you have to remember. Wn equal to exponent minus j 2 pi over capital N. And using Euler relation, you know that cos 2 pi over N, this one is minus j sine 2 pi over N. So this is the important equation in chapter 5. Okay, make sure you remember this equation before we proceed to other. Okay, let's continue with slide number 9. Okay, slide number 9 is on matrix form of DFT pair equation. So for you to understand this one, you have to really remember about your linear system subject. Okay, so basically this one is all about the matrix calculation. Okay, to solve DFT, one of the technique is using matrix multiplication. Okay, so for you to answer this one, for you to solve your matrix, okay, of course you have to remember this equation. N from 0 to k capital N minus 1 S N W and Kn. Alright, so this is actually your analysis equation. So your Sn is coming from the question. Okay, let's say your Sn is equal to 1, 2, 3. The range is from 0 to 2. So Sn is coming from your question. So you don't have to worry. What you have to worry is this one. W and Kn. So basically W and Kn is actually your matrix dimension. Alright, so let's say if you have, for example, 0 to 2, so you have 3. So the matrix is 3 by 3 matrix. Okay, so 3 by 3 matrix means you have 3 rows and 3 columns. This is 3 by 3 matrix. So for you to build your matrix, WKM matrix is basically depend on your Sn length. Okay, your capital N length. Okay, your capital N value, your length sequence. Where to find your length sequence? It is coming from your Sn. Okay, so if let's say your range is from 0 to 3, then it is length 4. So when it is length 4, So your matrix dimension now, instead of 3 by 3, now it is 4 by 4. Understand? Okay, cool. Okay, next. Okay, if you look at slide number 10. Okay, slide number 10 is actually on how to find the value inside the matrix. Okay, so inside the matrix, we have W and Kn. So we have the matrix dimension something like this. Okay, so we have W and 0, 0, W and refer to your notes. Okay. So basically, this is the general matrix dimension for W and Kn. Okay, so that's why this technique, the matrix multiplication, is only applicable on finite line sequence. Why you need to have the finite value of your capital N. Okay, because of that, this matrix is only applicable on finite line sequence range. Okay, finite line value. Alright, so okay, now this is another headache. How to find the value of Wn00, Wn01, Wn blah 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 until Wn. Okay, let's see, we have our n range is from 0 to 3. So if let's say we have our Sn equal to 1, 2, 3 and 4, the range is from 0 to 3. So from here we know that your capital N value is 4. Alright, so basically from here we can find our Nkn. Okay, means from here also we know that our matrix dimension is 4 by 4. Okay. Okay, so now I'm going to teach you how to find the value for this matrix. Okay, so basically we have W for 0, 0, W for 0, 1. Okay, so now I'm going to show you how to find the value for W400, W401, W402, W403. Okay, so how to find this value? Definitely you have to remember the equation W400, sorry, WNKN is equal to exponent minus j 2 pi k n over n. Okay, so now let's say we have W for, okay, can I erase this part? Okay, you already copy this part. Okay, make sure you copy this one. Okay. Okay, let's say we have W400. So W400 is exponent j2 pi k. Okay, this one is 0 times 0 over, okay, your kn is actually this one. Okay, sorry, your kn is actually your 0, 0. So you have 0 times 0 over capital N. Capital N is 4. So this one is exponent 0. So exponent 0 is 1. So what you have to do is for the first column and first row, all the value is equal to 1. Why? Because of you have 0. 0 times 1 is 0, 0 times 2 is 0. That's why first column, first row, the value is always 1.